This is a reenactment of a colloquium that I gave on November 20th, 2019 for the physics department of the City College of New York. In 1935, the abstract of the colloquium was the following. In 1935, Einstein, Podolsky, and Rosen published a paper indicating some disturbing aspects concerning quantum mechanics, including the possibility of the violation of Heisenberg's uncertainty principle and instantaneous long-range effects subsequently named spooky action in the distance by Einstein. The EPR paradox has spurred considerable research since its publication, including some attempts to eliminate the paradox by augmenting quantum mechanics with hidden variables, modifications that were later ruled out by experiments. In this talk, I will review the various arguments of the original Einstein-Podolsky-Rosen paper and then turn to the entangled spin one-half system, which has become the quintessential example of an Einstein-Podolsky-Rosen paradox. I conducted Donkin experiments showing that the collapse of the spin part of the wave function cannot take place. This result has many implications for quantum mechanics. In this talk, I shall discuss, or mainly discuss, one of them, the resolution of the Einstein-Podolsky-Rosen paradox within the normal framework of quantum mechanics. This is an outline of the talk. So it contains 1, 2, 3, 4, 5 parts, and I'll discuss each one in turn. So this is the famous Einstein-Podolsky-Rosen paper published in Physical Review in 1935. Einstein, Podolsky, and Rosen considered two particles that interact for a while in a central location and then separate far away. In the center of mass rest ring, the momentum of the two particles are correlated, being the opposite of one another. One measures the position of the particle on the right and then measures the momentum of the particle on the left. From the measurement of the momentum of the particle on the left, one can deduce the momentum of the particle on the right. Thus, one simultaneously knows the momentum and position of the particle on the right in violation of Heisenberg's uncertainty principle. But not so fast. The measurement of the momentum of the particle on the left causes wave function collapse, according to Einstein, Podolsky, and Rosen. This must affect the wave function on the right too. Before the momentum measurement on the left, the momentum of the particle on the right could vary over a range of values. After the measurement, it only has one value. Since the measurement on the left affects the wave function on the right, the original measurement of the position no longer holds. And this is the way one gets around violation of the Heisenberg's uncertainty principle. Now, the wave function for this system can be expanded is a function of the position of the particle on the left and the position of the particle on the right. We use minus for left and plus for right. And it can be expanded in an eigenstate of momentum for the left particle. The coefficients depend on the coordinates of the right particle. So the expansion looks like the following. You sum over momentum. This is an eigenstate of momentum for the left particle. And these are coefficients that depend on the position of the right particle. If the measurement of the momentum on the left is k, then according to Einstein, Podolsky, and Rosen, and the thought in general at the time, is that you have wave function collapse. So of all these terms, only one remains, and it's given by right here, where The momentum of the particle on the left is k. But one can wait for the two particles to be separated by a very large distance and arrange for the two measurements to happen almost at the same time. Then the measurement on the left must affect the particle wave functions on the right faster than it takes light to travel from the left particle to the right particle, which seems to violate special relativity. Einstein called this spooky action at a distance. Now, here's some opinions about this problem. A, this is a serious problem. There's something wrong with quantum mechanics, or quantum mechanics must be modified, and this led to hidden variable theories. B, this is very disturbing, but we must accept it. C, this is the way that quantum mechanics works, and it really isn't not that worrisome. D, somehow things work out and there is no paradox. E, quantum mechanics is a mystery and we don't really understand. Now we turn to the entangled spin 1/2 system. This was introduced by Bohm in 1951 in a publication of 1951. And it involves two spin 1/2 particles that are produced in the central region, and then one goes to the left and one goes to the right. We'll make this a specific case. Imagine that we have a source for electron-positron pair at some location, that the electron shoots off to the left direction with a velocity v, and the positron shoots off to the opposite direction with the speed v also. And then on the left, we have a measuring device to measure the spin. And on the right, we have a measuring device to measure the spin. And the assumption here, or if you consider a situation where it's the particle, it could be the source of this, could be a particle with angular momentum 0 in the rest frame, then the spins will be in an angular momentum or spin 0 state. The spin 0 state is given by the upspin of the electron, indicated by the minus here, the downspin of the positron, indicated by the plus here, minus the spins in the opposite direction. That is down for the electron and up for the positron. Here we're measuring everything in the z direction in spin space. So here's how the EPR paradox for this entangled spin 1 system works. One measures the spin of the electron in the z direction, over on the left here. Just before the measurement, the spin of the positron could be up or it could be down. If the measurement of the spin of the electron is up, then the spin of the positron must be down. If the measurement produces an electron spin indicating it's down, then the spin of the positron must be up. That follows from the form of the wave function. Now, there are seemingly two possible paradoxes here. The first one actually isn't a paradox, and the second one is the one that produces a spooky action at a distance. So let me describe the first, that might seem like a paradox, the first one. From the measurement of the electron spin on the left, one immediately knows the spin of the positron on the right. So it seems like knowledge has traveled faster than the speed of light. Second, the measurement of the electron spin on the left appears to have forced the spin of the positron to take on a particular value. And this also can happen faster than the speed of light. And Einstein called this, or this paradox, is the spooky action at a distance. So the resolution of one is quite simple. The key thing is, it appears here, here's the setup. And the key thing is that there's a moment in the past where the experimentalists, the two experimentalists, the one on the left and one on the right, decided what would happen during the experiment. They knew that they would produce a spin zero particle, and they agreed to measure the spin, one to go to the left and one to go to the right, and measure the spins of the electron and the positron. So that's this event in the space-time diagram. So one of them went to the left, set up this equipment on the left. The other one set up this equipment on the right. And then the experiment happened somewhere here. The electron went to the left, the positive on the right, and they made the measurements. The key point here is that they agreed to something that is within the light cone of the experiment, all that happens during the experiment. And because of that, they have knowledge that the spins are correlated. And so it's for that reason they knew the correlation ahead of time. And for that reason, the fact that when the experimentalist on the left measures the spin of the electron to be up, that he immediately knows that the positron spin must be down, there's nothing paradoxical about that. To really make this clear, you imagine that they don't discuss completely the setup. One is told to go to the left and measure an electron spin, and the other's told to go to the right and measure a positron spin. And they don't know that the spins are correlated, that they've been set up that way. So over here, the experimentalist measures the spin to be up, and then he doesn't know, he can't conclude anything about what's going on with the positron spin. So it's very clear that this event leads to the correlation and leads to a way of having knowledge being transferred instantaneously, and this doesn't violate a special relativity. Now, the definition of Copenhagen spin 1/2 measurement here is that we're going to have the measurement force wave function collapse. So let a particle be in a linear combination of spin Z states. So we have the spin 1/2 particle is a linear combination of up and down spin, which is given here. The probability of having upspin is the absolute value of A squared. Probability of having downspin is the absolute value of B squared. If the device measures the Z component of spin to be up, then the definition of the Copenhagen measurement is that at some point during the measuring process, the state becomes purely up if it's measured to be up. And this is achieved by destroying the down component of the spin. That is, this second term goes to 0, and this term becomes up with a coefficient of 1. Similar statements hold when the device measures the spin to be down. So in the case where it measures the spin to be up, we have wave function collapse to the upspin case. Now, a measurement involving wave function collapse of the spin part of the electron wave function causes aspect 2 spooky action and distance of the Einstein-Podolsky-Rosen paradox for the entangled spin 1/2 system. Because if you measure the spin to be up, then the wave function collapses to this term. Now, it could be that you measure the wave function electron to be down, and then it collapses to the second term, namely the electron spin is down and the positron spin is up. Each of these can happen with 50% probability and affect the spin wave function of the far away positron. So by doing a measurement on the spin of the electron, we've affected the spin of the positron very far away and faster than the speed of light. Now, I'm going to discuss some Gedanken experiments that rule out wave function collapse for the spin part of the wave function using this entangled spin 1/2 system. The first thing is that angular momentum can be violated. Assume that the initial state is an eigenstate of angular momentum with values of J and with the total angular momentum associated with J and total angular momentum in the Z direction being J sub Z, as measured at the spatial point where the pair are created. The initial state is something of the following form. This has total angular momentum 0, and if this is to have quantum values J and Jz, then psi, the wave function, which includes the position of the electron and the positron, and the equipment used to measure the spins. That wave function, the angular momentum content of that wave function must be J and Jz in order for the initial state to have angular momentum, quantum numbers J and Jz. When the Copenhagen spin 1/2 measurement of the electron is performed, the wave function collapses to either the first term, namely having spin up for the electron and spin down for the positron with some final state wave function, or to the opposite. If the electron spin is measured to be up, that's this case, then Jz can equal, the final total angular momentum can be equal in the Z direction, can be equal to Jz if this final wave function has angular momentum in the Z direction of J sub Z. But it cannot be a wave function, eigenstate of J squared. This eigenvalue needs to be J times J plus 1. And it is easily checked that J squared applied to this produces terms proportional to 2 up spins and 2 down spins and up and down spins that cannot cancel among themselves. One needs only this term to equal this, to be an eigenstate of total angular momentum with value J. And this cannot happen. What needs to be there is a term in which this appears, and there's a wave function involving these other components that has Jz equal -1. And another term like this, where the 2 spins point down, and the wave function involving with all the other degrees of freedom has Jz pointing up, in order to get something that combines to give you angular momentum, total angular momentum with a quantum number of J. Intuitively, the one way to see this is if the final state in the up, when you measure the electron spin to be up, is this, you can write it as a sum of 2 terms in this way, where the first term you use a plus and the second term you use a minus, and then the second terms cancel. This term has angular momentum 0. So psi prime has to be an eigenstate with eigenvalues J and Jz. The second term involves angular momentum 1. And when you combine something with angular momentum J and angular momentum 1, you get things that involve total angular momentum quantum number J plus 1, J, and J minus 1, and not just J. So it's impossible to preserve angular momentum under this wave function collapse for this system. Now here's another argument, and this involves causality and wave function collapse compatibility. So we're going to modify the spin 1/2 entangled system in the following way. The left measuring device is going to be moving at a relative speed to the left. For example, we could take this measuring device to be moving at 95% the speed of light. And we can also take the electron and positron speed to be relativistic also, that each of the speeds are 99% of the speed of light. Then we also adjust the positions so that initially the measuring device on the left is closer than the measuring device on the right. So in light seconds, the analog of light years, but involving light seconds, we take this device to be a half a light second away and this one to be 1 light second away. Now, you can check the following is true. In the right frame's rest frame, over here, the positron, measurement of the electron spin over here happens almost 11.5 seconds after the right experimentalist measures the spin of the electron. So when he makes his measurement, the measurement on the electron is going to happen in the future and can't affect his measurement. In the left experimentalist rest frame, the measurement of the positron spin happens almost 3.9 seconds after the left experimentalist measures the spin of the electron. So when the experimentalist makes his measurement on the left over here, the measurement of the positron is not going to happen until almost 4 seconds into the future, and therefore cannot affect the measurement of the electron spin. So with wave function collapse, the measurement by the experimentalists on the right of the positron spin, so when we measure the positron spin, it may collapse to spin down for the positron, meaning the electron spin is up, or to the positron spin being up and electron spin being down with 50% probability. Now, this collapse cannot be affected by the measurement of the spin of the electron on the left because that measurement will happen in the future. So whatever happens over here, it can't affect the decision of which of these happens. The same is true for the experimentalist on the left, measuring the spin of the electron. When that measurement is made, half the time the wave function collapse happens to this term, and half the time it happens to this. And that means, and these can't be correlated. So half the time, this one will collapse to this spin state, and this one will collapse to this spin space, or vice versa. And therefore, half the time, the wave function collapse won't be compatible. Now we have another Gedanken experiment involving the violation of Heisenberg's uncertainty principle for spin 1/2. It says that for a spin 1/2 object, the uncertainty of the spin measuring the spin in the y direction times the uncertainty of measuring the spin in the z direction must be greater than this constant. So one cannot simultaneously measure the y and z components of a spin 1/2 object. So we arrange in this case, we arrange we can set up the same situation as before with moving objects, but we arrange the right experimental. So we arrange the situation as in the previous transparency. So we're going to have this moving relativistically away and being closer, and then the electron-positron pair will be shot out at 99% of the speed of light. So what we do is we arrange the experimentalists to measure the spin on the positron on the right side to be in the y direction. Then we measure, then we know the measurement of the z component, the y component of the positron spin for certainty. Now we can deduce the y component of the spin for the electron with certainty because of the anticorrelation of spins. The wave function is not only uh, of this form when the axis of spin quantization is in the z direction, but it turns out it's always of this form, no matter what axis it is, including the y-axis. So if the spin of the positron is measured in the y direction to be up, then the spin of the electron must be down. And if the measurement of the spin of the positron is down in the y direction, the spin of the electron must be up in the y direction. And now, now you make the measurement of the electron in the z direction. And from the direct measurement of the electron, you'll know its spin in the z direction with certainty if there's wave function collapse. And that means that you have a violation of this uncertainty principle because both of these have been used to measure the spin of the electron precisely in the z and y directions. This is very similar to the Einstein-Podolsky-Rosen paper, except that we're using spin. And we've arranged the system so that wave function collapse cannot affect each of the other two's measurements. So here I have a cartoon by Schwartzstrawn, and it says, stocks post gains today on news that the Heisenberg's uncertainty principle was found to be violated. So when you hear this talk, maybe tomorrow there'll be a gain in the stock market. Just joking, of course. Now we come to a violation of quantum mechanical unitarity. This is well known that wave function collapse violates quantum mechanical unitarity. So I'll just review what that means. We assume that the wave function, our basic starting point, is that there is a generalized Schrodinger equation that governs the wave function of the system, so that the derivative of the wave function with respect to time up to the constant I in h bar is equal to the Hamiltonian times the wave function. Now, if the wave function is known at time t0, then at any later time, tf, a final time, you know the wave function, and it's given by a unitary operator that just multiplies the initial wave function. And that unitary operator is just given by the time-ordered product of the exponential I over h bar times the integral of the Hamiltonian during that time interval. This is a unitary operator. It preserves norms and inner products. So if you have wave function 1 and you know it at times t0, and it's governed by the same Hamiltonian, governed by this Hamiltonian h, then you just apply the unitary operator and you find its value at a final time. You can do this with a second wave function. Given any initial wave function, psi 2 at times 2, 0, you're assuming it obeys the same Schrodinger equation with the same Hamiltonian, the same unitary operator applies. Then you have the following properties because this is a unitary operator. The norm of psi 1 is preserved. Its norm at time equals 0 is the same as its norm at the final time. And this property, of course, is important in preserving probabilities in quantum mechanics. The same is true for the second wave function. You also have that the inner products are the same, namely that if the inner product of psi 1 and psi 2 at the initial time is some value, then that's also preserved and will be the same at any time in the future, and particularly at some final time. Now, we'll assign a psi 1 to be the first component of this entangled wave function. So this is the spin part of the first, and psi here initially is, you recall, contains the spatial degrees of freedom of the electron and the positron and the coordinates of the measuring device, the quantum degrees of freedom of the measuring device. And that's common to both initially. And this we call the second wave function. Now, when we make the measurement, let's assume that we have wave function collapse to the first component. Then this will evolve to some prime wave function. And the second coefficient will be 0. So suppose the spin measurement preserves unitarity by having opposite spin component flip. So one way to accomplish this would be to assume that, well, we're going to assume that what happens here is psi, we initially had a psi A times up and a psi B times down. And that became psi A prime up and psi B prime up, so that we ended up with the spin being up. So we assume that we can achieve wave function collapse respecting unitarity in this manner. Then unitarity requires that the A prime, the final wave function, A prime here's norm has to be the same as the initial one. That this norm has to be the same as this one. And because this, the inner product of this with this is 0 because of the spins, and now the spins don't do that, we need to have that the final wave function associated with the A up component and the one with the B component have to be orthogonal. So then there's no spooky action at a distance in this case, because this wave function, if you work it out, here we're applying the measurement to the electron and ending up with an upspin case for the electron spin. And then this term becomes psi prime A times the spin being up with a positron spin being down. And the second term, when we make the measurement of the electron spin, becomes the second term. And we've now the spin of the positron still contains both up and down spin. So the positron spin still has 50% chance of pointing up and 50% chance of pointing down. The positron spin is not affected by such a measurement. And so we avoid, there's no spooky action at a distance. So wave function collapse is causing all these horrible things that I just mentioned here. But what I did here before is I assumed unitarity, but I just made the wave function's spin to be up for the second case here. So here's the resolution of the Einstein-Podolsky-Rosen paradox within quantum mechanics. So given that a Copenhagen spin 1/2 measurement on the entangled spin 1 system not only violates quantum mechanical unitarity, but in Gedanken experiments can also lead to a causality contradiction and violate both conservation of angular momentum and the Heisenberg's uncertainty principle. The reasonable conclusion is that the that wave function collapse of the spin part of the wave function cannot happen for the system. If it cannot happen, then a measurement does not cause the spin part of the wave function to collapse either to this term or to this term. And there is no spooky action at a distance. And aspect 2 of the Einstein-Podolsky-Rosen paradox is resolved. Now, okay, so here's the result if unitarity holds. If the spin measurement on the left obeys quantum mechanical unitarity, then that measurement cannot affect the spin of the positron on the right. Quantum mechanical unitarity alone is sufficient to rule out spooky action at a distance. And that's what we just showed before. The proof of this can be found in the version 1 of the archive paper that I provided in the physics section of the archive. It's entitled, here's the archive number, and it's entitled On Wave Function Collapse and the Resolution of the Einstein-Podolsky-Rosen Paradox for the entangled spin 1/2 system. There's also future versions of that paper which have additional results. And the title might have changed, I forgot here. So there is no Einstein-Podolsky paradox in quantum mechanics if wave function collapse cannot happen. And that only holds for spin 1/2, but it will hold for other measurements too. So we come back to those opinions. The answer is things, among the 5 possibilities, the 5 opinions, things do work out, and there is no paradox. Here's a cartoon I got from the internet. Hey, after all these complicated calculations, no problem. So now I'd like to talk about some of the consequences for measurement in quantum mechanics. So the first thing is, let's ask, is there still a problem with Heisenberg's uncertainty principle with relativistically moving devices? So if in a single measurement, one definitely determines the spin, then the wave function collapse must occur. So what I showed before is that there isn't, let me see, what am I doing? Let me just go ahead here for a second and see what. Okay. So there is no problem because both spin states of the electron still are maintained. So you don't know the spin with certainty neither in the z direction nor in the y direction. So you don't have a problem with Heisenberg's uncertainty principle. Now, if in a single measurement, one definitely determines the spin, then the Copenhagen wave function collapse must occur. Okay, now I'm assuming here that if in a single measurement, one definitely determines the spin, then Copenhagen wave function collapse must occur. So the logic here is if A, then B, where A is this statement and B is this. Now, if that is true, then not B implies not A, and you get the converse Copenhagen statement. If wave function collapse does not occur, then a single measurement one cannot definitely determine the spin. And this is obvious because if if the spin is a linear combination of these two and it doesn't collapse to one of these, then there's still uncertainty in the spin being up or down. And so you cannot definitely determine the spin. There's also another measurement rule, and that is if in the Copenhagen picture, wave function collapse is needed to explain an experimental result, then multiple measurements are necessary to determine the quantum state. But if a measurement does not need wave function collapse to explain it, then a single measuring event suffices. So let's consider this second case here. Suppose we're going to measure the spin of by Stern-Gerlach. So what happens then is if the spin is up, then the spin 1/2 object rises above the z = 0 plane here. under the influence of gradient magnetic fields. And if the spin is down, it ends up below the plane. And if you see a flash above the plane, you know the spin is up. And if you see a flash below the plane, then you know it's down. Now let's assume that the spin is only up. Then what happens is you see a flash above the plane. The spin is up. You didn't need wave function collapse to explain the observation that the spin is up. And so one measurement suffices to determine the spin. Now let's consider the situation in which the spin in the z direction is a linear combination of up and down spin. And we'll assume for simplicity that's 50% chance of being up and 50% chance for being down. Then how does one measure the spin state using Stern-Galerk? Well, what we learned about, let's see. Okay, so let me explain what goes on here. So what will happen is, in the case where it's a linear combination, we may see a flash up and we may see a flash down. But in either case, we haven't determined the spin of the wave function. What we need to do is to make many measurements. And if we do so, we'll see 50% of the time the spin is up and 50% of the time the spin is down. And at that point, we would know at least some of the structure of the spin state. It would involve the sum of two terms with coefficients whose square are equal to 1/2. And by doing it in different directions, eventually you could determine the spin. But it shows here, it illustrates this. If so we needed wave function collapse to explain this situation. When we saw it go up, the person that believes in wave function collapse will say, oh, we need wave function collapse to believe this. So in that case, we need multiple measurements to actually determine the form of the wave function. So what we've learned about quantum measurement, in my opinion, is even more important than the resolution of the Einstein-Podolsky-Rosen paradox. When an experimentalist tries to measure spin and the signal indicates that it is up, the experimentalist cannot be sure that the spin state is up. In general, multiple measurements are needed to determine the spin state. If wave function collapse cannot happen in general, then similar statements hold for other types of measurements on quantum systems. Statements such as, in a single measurement, when a single signal from a signal suggests, from a measuring device, suggests a particular quantum state, one cannot be sure that the system is in that state. The uncertainty associated with quantum mechanics at the microscopic level is transmitted to uncertainty in measurement at the macroscopic level. Multiple measurements may be needed to determine the state. So, wave function collapse is misconception. It is to quantum mechanics what the flat Earth theory is to the question of whether the Earth is round or flat. The idea that macroscopic measurements of quantum systems causes collapses of the wave function is a misconception that leads to the Einstein-Podolsky-Rosen paradox, and two, the incorrect belief that macroscopic measurements on quantum systems involve no uncertainty. And that's the end of the talk. Thank you.